Hello, everyone. So, in this next section, we're going to talk about something called a critical value approach to hypothesis testing. This is sort of the first wave of how do we go through and actually set up the test. What does that test mean? So, let's talk about what this means critical value. Critical values are associated with z values. Right, remember the z value is the distance in terms of standard deviations you are away from the mean. And if we're going to set up a criteria for rejecting a null hypothesis, essentially the way that it's going to work is this. Either we're going to reject or fail to reject the null hypothesis. And sort of the dividing line that we're going to use right here is whether or not that mean that we get from our sample or that mean that we get from our, from some other description, that mean falls within a region that is either within a rejection region or not. In other words, what we're going to say here is this is kind of the logic. Let's say that, again, we're going back to our mayor of Providence saying that it's $50,000. So we take a sample of 100 residents of Providence and we find that the mean is $49,500. So what do? Well, we look at whether or not we have enough evidence to reject that mean based on a normal distribution. We take our normal distribution and we say, well, okay, if $49,500, right, is the difference between that and the population, the claimed mean, is less than, and divided by the standard deviation, right, that's our z-value. Let me get your z-value again here. Z-value, right, the z-value, remember, is equal to the sample mean minus the population mean, right? So in this case, we're actually going to take our claimed mean and divide that by our sample over the square root of n, right? Remember that was our sampling distribution. Let's say that if we find out that that z-value that we get from our sample is down here, it's less than, right, associated with a 0.05 probability is the z-value negative 1.645 from our table, right? So let's say that we find this as our z-value. Well, if that z-value is less than negative 1.645, well, yeah, we've definitely got enough evidence to reject the null hypothesis. But if the z-value is not, right, let's say the z-value is over here somewhere, right, then we don't have enough evidence to reject the null hypothesis. Right? So this is 1.645 kind of becomes our criteria. It's a dividing line between z-values that are less than whatever our rejection is or greater than. Right? So what we're looking to do here is we're looking to find out whether or not we get enough evidence based on a sample, let's say, as to whether or not we have doing that. Right? Here's this is a example from golf driving distances, but it doesn't matter, right? Basically, this is what we're doing. All right, what's the logic here? A rejection region, a non-rejection region, and critical values are the values of the rejection region. It's the set of values of the test statistic that leads to rejection of the null hypothesis. So we're looking for that area under the curve. Remember, the area under the normal curve is a probability, right? It's a cumulative probability. So we said those set of values that make up that rejection region, that's what's going to lead to rejection of the null hypothesis. We have a non-rejection region, which is the region that's not within that rejection region, essentially. So we don't have enough evidence. And the critical value is that dividing line, right? The z-value that falls somewhere in there. And so we want to know how to pick that z-value based on whatever critical number we're looking for, right? So we said there was two kinds of tests, right? And it depends on our alternate hypothesis, right? If our alternate hypothesis goes that the mean, the population mean, is just not equal to our standard deviation, then this is the test that we're using. We're saying that we're going to reject in one of two regions, right? If the mean is too low or if the mean is too high, right? And if we don't have a value that falls our sample mean within a rejection region, then we don't have enough evidence to reject, so we put that in the middle somewhere. Now, if our alternate hypothesis, this is why we're calling it a left-tail test, if we said that our mean is actually less than the claim, right, then that puts our rejection region off to the left of the middle of our distribution, and that's why we call this a left-tail test, because we're looking to see whether or not the rejection region fell within left tail. We don't care if it's higher, right, if this is our point of view. We're just interested in whether or not it's left. And of course, conversely, we also have the right tail test, which is everything to the right of that mean, right? So if our alternate hypothesis here is the one that says that the mean is greater than the claimed mean mu0, then yeah, then we're looking for that one. And again, we don't care if it's less in this case, we just care as long as it's not more, right? And that's sort of an important thing. All right, so there's all kinds of creative ways of stating that, and you have to be very careful in the way that you're reading some of these problems that are given in the textbook. But this is what we mean by left tail, right tail, or two-tailed tests. All right, so what do? We need to find these critical values. And remember, we talked about a critical value being associated with a value alpha. Alpha, if you have a curve, and let's say that we have our mean curve right here. Alpha, the level of significance of our test, is associated with that idea that we dealt with last week when we had 1 minus alpha as the area over here, right? This was our confidence interval, by the way, right? Whenever we were doing a two-tailed test, we had a confidence level, remember that? We had a confidence interval. And our job last week in Chapter 8 was to look at whether or not the mean fell within that confidence interval or not, right? If it didn't, then we say, well, the probability of not having that is alpha. And actually, we divided it in two ways, right? We say alpha, right? If alpha is equal to 5%, right, for a 95% confidence level, then we look to see whether or not there's a 2.5% probability that we are less than the mean, or a 2.5% probability that we're greater than that mean, right? So this alpha level now becomes sort of the important piece to us. And the critical value must be chosen so that if we are doing that, right, if you're using the critical value method right here, we're looking for critical values that separate the non-reject from the rejection region. That is, that separates our confidence interval away from the others. And this has a lot to do with the way that we deal with that, right? So we're looking for, if it's a two-tailed test right here, whether or not we have a z-value associated with alpha over 2, right? Because if our significance test is alpha equals 0.05, let's say, right, and we've got a 95% confidence level, then we're going to have an alpha over 2 of 0.025 to the left and 0.025 to the right. Now, we oppose that to one of our one-tailed tests. In the one-tailed test, all of the probability is either in the left tail or the right tail. So if we say a 5% probability, then we associate our rejection region with a probability associated with 5%, right? And that rejection region becomes our 95% confidence interval only on one side. All right, so slightly different in a way than what we did last week, but the logic still remains the same. All right, more to come in our next section.